Alright, in this video we're going to consider what is called time-to-event data, which borrows heavily from methods developed primarily in the medical literature for doing what's called survival analysis. Some of the examples of time-to-event data are the age at death, when an individual dies, the time it takes for a searching forager to leave a patch after entering a patch, the time required to find a prey item while a predator is searching within a patch, and also in the industrial literature, the failure of a component of a piece of machinery. All of these examples share a few features. One is the data is continuous, but bounded at zero, and so there's not possible to have negative response variables. Sort of four core concepts that are important to think about when you're dealing with this kind of time-to-event data. The first is censoring, which arises for a whole bunch of different reasons, but basically means that you don't know exactly when the event occurred. Survivorship is the proportion of individuals that are still at risk of an event, and at any particular point in time. The age at death, or the time of the event, that's the actual response that we're looking at. And then what we're going to try and model is the instantaneous rate of death, or what's called the hazard rate, as our predicted outcome. So here's an example of a couple of simulated survivorship curves. And what you can see is that they all share all of these sorts of curves share a feature. They start at zero, and time increases. And on the y-axis, they start at 1, and then the proportion that are still at risk falls over time until eventually the event has occurred to everyone in the sample that's being followed. So let's first think about censoring. Censoring arises because you fail to observe the event for one of your subjects. So for example, the experiment might end, or the subject might disappear. This is particularly true in medical experiments, where for one reason or another you're unable to contact one of the experimental subjects. They've moved, they've changed their phone number, they've decided not to participate any farther in the experiment. And the question is what to do with these observations where you failed to observe the event. And so one typical thing to do is to remove those observations. And the difficulty with this is that it's going to bias our results against those events which, in fact, the event might have occurred if we had waited long enough. And similarly, we could assume the event occurred at whatever the maximum time was, and that's going to cause the same sort of bias relative to what's really going on. Okay, what we've got here is some simulated data. The blue lines are the events are occurring at half the rate at which they're occurring during the red lines, and you can see that by the time we get out here just past 50 time periods, both of the groups have reached zero. Then what I did was randomly select some of these observations to be censored. In other words, what was the last point in time at which we observed them. And what you can see is that this sort of changes the scope now. So the censored observations are marked with pluses along each of these curves here. And so what's happened is that these curves, instead of dropping all the way down to zero, now sort of flatten out right at the end point here. But there's censoring events that have taken place prior to that as well. And so this is a table of the average time. If we simply treated this as normally distributed data and calculated the average time to event, what would we expect to see? And so what you can see is that there's, if we use the maximum value, we get 24 and 17. If we use the minimum value, or simply throw them out, the censored individual ones, it drops. And actually the theoretical values are quite a bit higher than what you would expect, than what we've observed here. And if we do some model fitting, which we'll come back to in terms of how to do this later on, throwing out the censored points gives us curves that are too high. Okay, we overestimate the rate at which, or underestimate, sorry, the rate at which events are occurring. If we use the maximum observed, we do better, but again, as we reach the end, again, we're starting to overestimate the rates at which events are occurring. And finally, if we treat them as censored, then in fact we can get an unbiased estimate across the entire range of the data. So we'll come back to how we're going to go about doing that later on. But essentially it means we don't discard the information on those individuals that are lost to the study. All right, let's take a look at the concept of survivorship now. Survivorship is simply the proportion of individuals that are alive or for whom the event has not yet occurred at time t. And so we can think of this s, this function s of t, where big T is the time the event occurs and little t is the present time, is simply the probability that the event has not happened yet. And it's going to be equal to 1 minus f of t, where f of t is the cumulative distribution of the time of the event. And that's what we've been plotting up until this point. It's essentially the survivorship curve, or 1 minus the cumulative distribution. And we're often then, as a result, interested in the age at death, as we calculated before. What's the average age at which individuals in a group are dying? And so this is the distribution or density of events per unit time, and that's given as the derivative of this cumulative distribution function. Finally, another function that we're interested in survival analysis is called the hazard function, and this is simply the instantaneous rate of the event occurring at a particular point in time t, conditional on surviving to time t. So the event has not yet occurred. What is the rate at which it occurs right now? And you can calculate this as the density of the events at time t normalized by the probability that the event has not yet occurred, which is simply our survivorship function. So let's look at these three functions for a simple distribution, the exponential distribution. In the exponential distribution, the density f of t, given some rate parameter, is given by this simple function here. So lambda is our rate at which events are occurring, e to the minus lambda t, and that's going to be the distribution of events occurring at rate lambda. The survivorship function then is going to be the integral from t to infinity of that density function, and that turns out to be even simpler. That's simply e to the minus lambda t. And our hazard function is then the ratio of these two things, and so the hazard function for an exponential distribution is simply lambda, because it's the ratio of these two functions. And so notice that the hazard function for an exponential distribution is in fact constant. That means that the probability of an event occurring is not changing as a function of time. And this is why the exponential distribution is sort of your simplest possible representation of random events occurring in time. It is also called the memoryless property of the exponential distribution, because it doesn't matter how many events have already occurred, only matters what the rate is. And in an exponential distribution then, the time at death, the expected time at death, is going to be 1 over lambda. So let's look at plots of these functions now for two different values of lambda, 0.2 or 0.02 and 0.04. Here are the density functions. So if the rate is decaying exponentially, or the density, the distribution of events is decaying exponentially towards 0, and it's half as likely to occur at this particular point in time. And it's not until out here that you get fewer events occurring at the higher rate, but that's only because you've run out of individuals for the event to occur to. The survivorship curves look like this, so they both start out at 1 now, and then they decay exponentially towards 0, and the hazard functions are, of course, flat lines. So 1 over lambda, the expected time at death for the blue line, is going to occur at 50. For the red line, it's going to occur at 25. There's another distribution that we can think about, a sort of a generalization of the exponential distribution. And it adds another parameter for us. So we've got, previously we had a scale, the rate parameter. What we have with the Weibull distribution is also a parameter that represents the average time at death. We're going to call that the scale parameter. And then we have an additional parameter called the shape parameter, which tells us how fast the rate is changing as a function of time. When the shape parameter is equal to 1, we get an exponential distribution. When the shape parameter is less than 1, we get a rate that is decreasing with time. So that gives us the blue curve here. So we have a high rate early on, and then the rate decreases. And that gives us a particular shape to the survivorship function, and you can see that the hazard function is now also no longer constant, it's a decreasing rate. When the shape parameter is bigger than 1, we get an increasing rate of events, and so that causes the density distribution to flip around. And we also get a different shape to the